Buenas tardes. Bienvenidos al Seminario Fronteras de la Energía, organizado por el Instituto de Energías Renovables de la UNAM. En esta ocasión tengo el gusto de presentar a la profesora Sylvie Lorente de la Universidad de Villanova en Pensilvania, y como cortesía a nuestra invitada voy a presentarla en idioma inglés. Professor Sylvie Lorente is the William M. Brown 8487 Endowed Chair Professor in Mechanical Engineering at Villanova University, Pennsylvania, since June 2024. She is the Senior Associate Dean for Research and Innovation in the College of Engineering. She is also professor at the National Institute of Applied Sciences, University of Toulouse, France. In 2019, she joined Villanova University as College of Engineering Chair Professor in the Department of Mechanical Engineering. She is a member of Academia of Europa and a member of the Scientific Council of the European Research Council. She is the Editor-in-Chief of Energy Conversion and Management and a member of several editorial boards, including Nature's Scientific Reports. Sylvie has a passion for flow architectures and works on thermal design, energy storage, vascularized structures, porous media, biological flow networks, urban design, and organizations. Together with her group, she uncovers the engineered and biological hierarchical flow pathways that endow complex systems and efficient properties and behaviors. She is the author of 7 books, 10 books chapters, and more than 230 peer-reviewed international journal papers. She is listed among the top 2% most cited scientists worldwide since 2017. Professor Laurent, thank you very much for accepting the invitation, and you may start with your presentation.
Okay, thank you. Hola y buenas tardes. Encantada estar aquí y presentar mi trabajo de investigación. Let me try now. I immediately switch to English and let me share my. Where is it? Okay. Perfect. And now let's see. Can you see my screen? Is it working well? Okay. Okay, very good.
Yeah,
So yes, let's discuss a little bit the type of work that we were doing related to energy efficient systems with a little specific angle of attack, which is through a flow architectures. So you presented the work I do already. So let me immediately switch to what I mean by flow architectures. Since we are dealing with experts in thermodynamics, I'm not teaching you anything by saying that things flow from high potential to low potential, and that's the very meaning of the second law of thermodynamics. Now, we know that flow happens if there is a potential difference. We need this potential difference, which in the example of the picture I am showing here is a difference in altitude. Every time there is a potential difference, there is a flow. Every time there is a flow, there are some resistances to this flow, and that's what we are interested in. On a side note, we can also complete this idea by saying that if there is no potential difference, there is no flow, which means that everything is in equilibrium, and that's another definition of that. Wrong side. So the way we work is that we question and we try to develop theories so that we can predict and design with purpose. So the picture that you see here on the left-hand side is showing a picture taken from a satellite of the delta of the Lena River. That's a natural system. On the right-hand side, you have an engineered system. That's a flow architecture that was developed for certain purposes. We are not mimicking nature. When we look at nature and we copy, this is mimicking, and this is a biomimicry, which is a branch of investigation. Interesting, but not what we are interested in, because we really want to understand, develop theoretical approaches which help us predicting and designing systems, because we are engineers. And here are some examples of flow architectures. And I chose those pictures because I want to convince you that those flow architectures are multi-scale and happening everywhere we look at. So from the blood network that you see on the left-hand side, tiny, tiny scale, to on the right-hand side, the roots of a tree, a larger scale. In this case, we go from blood flow distribution to a network which is favoring access for groundwater escaping through the trunk. So you see those are volume to point or point to volume flow architectures. And they exist whatever is flowing. It can be a liquid, a gas, it can be heat, it can be electricity. You could also think that ideas are flowing, but all those flows are happening through hierarchical systems. And if before I was showing examples of systems that we find in nature, here you have a designed system for a very typical engineering application, which is the cooling of electronics. And as a matter of fact, those tree-shaped architectures, which are designed through copper matrix, are here to control the electronic components temperature. And for the anecdote, this is being designed by our colleagues in Guanajuato that we were just discussing before the start of this presentation. This is based, if we are capable of looking a little bit, here, if you look here, you will read constructal flow pattern, which is exactly what we are discussing this afternoon. So the point is that those dendritic systems that you see here, the way of assembling flow channels, are predictable features. We discover them in nature. We know how to understand why they are happening and how they are designed. This is exactly what we are using and what I am going to present through different examples in the coming slides. The work is truly about defining flow configurations and understand that if we can change their shape, the way they are connected, so globally speaking, their architecture configuration, then the system will improve its performance. And we do this because we are decreasing the resistances to the flow and we are distributing the thermodynamic imperfections. So the three examples I would like to cover this afternoon are related to some of the most recent work that we do here on campus at Villanova. So we work on developing systems with the objective of creating isothermal compression processes. We also work on capillary networks for different types of applications. And we also work on the thermal management of batteries for either electrical vehicles or for stationary battery energy systems. So let's start with isothermal compression. Now, I will just as general introduction, I will start by saying that applications related to compressed gases can be found all over the world at every scale and in most engineering process. So, okay, so here you have the classical piston cylinder system that you see here on the left-hand side. During compression and expansion, different processes can be considered adiabatic, polytropic, or isothermal. And we know from thermodynamics that the isothermal process is the most efficient one. So that's truly the graph that we are looking for. Illustrated here through when plotting the work input as a function of the compression ratio for polytropic or isothermal processes. Same story on the right-hand side for the expansion work. Here's the application we are specifically interested in. Compressed air energy storage, CAES. The idea is to work to combine those systems with renewable energy, wind or solar, when intermittency is preventing to the actual full deployment of renewable energy to make power. So storage solutions are necessary because wind is not available every time it's needed. Sometimes more power, too much power will be created and therefore is lost if storage is not available, and vice versa. Wind may not be available at a time when power is needed by the grid or by the users. So this is why storage is necessary, and compressed air energy storage is one of the solutions. The idea being to use the energy coming from renewable to compress air, store air either underground or in tanks, and next, when power is needed, expansion happens, and power will be produced and sent to the grid. Those systems exist, and there are actually some existing plans. The very first one, if I'm correct, was built in Germany, and there is another one in the United States, in Alabama. The different types of compressed air energy systems are diabatic, adiabatic, and isothermal, should anybody be capable of producing them. Right now, because the temperature of the compressed gas increases with the increase in pressure and vice versa during expansion, more work is needed to run the system. And typically today, in addition to the piston itself, an additional system will be needed in order to reduce the temperature of the gas during compression and increase the temperature of the gas during expansion. On this table, you have the typical expected round-trip efficiency of the three existing compressed air energy storage systems. So going from the lower efficiency, which is the one that corresponds to the existing power plant today, only 55%, all the way up to theoretically it should be 1 for isothermal compression. So that's a little bit of the context. What we are trying to do is to find solutions allowing to come as close as possible to isothermal compression. So we're trying to develop solutions that will allow to maintain the temperature of the gas constant during compression and during expansion. And we do this. I have an issue with my slides. Okay, it's okay. So we do this with liquid piston. So here in this drawing you have a comparison between the two types of piston: the typical solid piston on the left hand side and the liquid piston on the right hand side. So the liquid will be just pushed up, at a constant velocity and therefore compressing the gas in the chamber. We have not developed, I don't know. We were granted a patent with the ideas that we are developing. And I'm sorry because I see that I have an issue with my slides, so I will just explain to you what we are doing and what we have been developing. So we have this volume here, if you can see. It will be a laser pointer. Okay, so the volume which is available here is the volume of air, which will change as a function of the liquid is going up in this liquid piston. The idea is to insert within this chamber elements, solid elements that will be capable of absorbing the heat while the piston, the liquid piston, is moving upward and the temperature of the gas is increasing. So the idea is to have a solution that is absorbing the heat generating during compression. And this inserts that we proposed in the patent to put within the chamber are tiny elements made of phase change material. Those tiny elements, so like a wax, if you will. But so we know how to calculate the volume of phase change material that is necessary to absorb the heat generated during the compression in this liquid piston as a function of the velocity of the liquid piston, as a function of the compression rate expected. So we know the total volume of phase change material which is necessary, but that's not enough. If you put the volume without thinking about the configuration of this phase change material volume, the heat generated by the compression will not be necessarily absorbed by the phase change material. And the reason is that typically phase change materials have a very poor thermal conductivity. So even though their latent heat is capable of, on paper, in theory, of absorbing all the heat generated when the gas is compressed, because of this poor thermal conductivity, nobody can guarantee that the heat exchanges are going to happen. So that's why once we determine the volume of PCM that is needed, then we are going to give configuration, we are going to design the shape of the PCM inserts. The ongoing work right now consists in using tiny millimetric cylinders of PCM, which are protected by a metallic envelope. So you imagine a tiny cylinder, metallic cylinder, a very thin one, which is filled by the phase change material. We are filling the cavity, we are filling this entire space with those tiny cylinders assembled one with each other, which means that we are creating a kind of porous system, allowing the air to flow in between those cylinders connected together. So this is a design porous system through which the compressed air is capable of flowing and the heat generated by compression is capable of flowing. And we know how to design the thickness and all the geometrical parameters of those tiny phase change material elements so that we can favor the heat exchanges. So heat will be transferred initially by conduction from the surface of the PCM insert towards the inside of the PCM cylinder so that the melting front propagates, the phase change material melts, And by melting, thanks to latent heat exchanges, the PCM is absorbing the heat generated during compression. That allows to not to be entirely isothermal. I have to be honest, the very first results that we have show that we have, depending on the configuration, increases in temperature between 10 to 20 degrees Celsius. But nevertheless, so that's why we say that we are quasi-isothermal. At the end of compression, the result is that the gas is compressed, the temperature increase has been very limited, and then the gas is ready to be stored. And the other way around can happen. So when we want to expand the gas, the PCM, which was now in liquid phase within the tiny metallic envelopes for all those small PCM cylinders in this design porous system. So at the start of expansion, the phase change material is in liquid state. By letting the previously compressed and stored air entering into this air chamber, the temperature of the air will allow the solidification of the phase change material, which is in this case releasing the heat that had been previously absorbed. So we are right now submitting the paper, and if there is interest in the audience, do not hesitate to let me know at the time of the Q&As, and I will be delighted to send the paper once accepted. Now a few words about the capillary networks and why we are interested in them. So here in this work, we are designing capillary systems, which means that we are interested in transporting a liquid, which in all the studies that we have been conducted is water. And the idea is to try to understand for a given porosity how we should assemble the pore network so that we can pump the maximum volume, the maximum amount of water from A to B with the minimum effort. And applications are related to fluid transport, so only the fluid mechanics aspect, but also to cooling applications and two-phase flow applications for cooling of electronics, for example. So that was the very reason why we started to be interested in this. Here I'm showing you some elements of context. On the left-hand side, we see that on the abscissa, the heat flux, which is generated by electronic components, which is increasing over the years, requires novel techniques for cooling. Initially, for small values of heat flux, the thermal management was conducted through free convection. While the heat fluxes started to increase, free convection was not enough, and that's why forced convection was a solution, first with air cooling and then with liquid cooling, single-phase liquid cooling. But today, with GPUs and etc., the needs are such in data centers that single-phase liquid cooling is not enough, and more two-phase cooling solutions are being explored. And the idea is that, again, to take advantage of the change of phase, just like we were discussing previously with the phase change materials from solid to liquid. Here it's again a phase change, except that this time it's about liquid, and vapor. Okay? And the way it works, you have an example here on the right-hand side. At very small scale, porous systems are being designed so that the liquid will be pumped, so either with a pump or thanks to capillary forces, and the liquid will then penetrate the porous system and evaporate at the top surface of the porous element. The heat flux hitting the top of the system, of the porous material. Okay? So that's one example of application, and I am showing here another one. Same story, except that this time there is instead of having simply the heat flux hitting the top surface of the porous material, we are dealing with a hot stream. But the cooling system is absolutely similar. In this example, you see that we have a water chamber on top of which there was this porous element that is represented here by those tiny spherical elements. And because of the very small spacing between the spheres, the liquid, which was water in this case, the liquid will move upward thanks to capillary suction. When the liquid reaches the top surface of the porous system, it will evaporate because it will be in contact with the region of a hot temperature. Okay? Here, and you have a zoom here on what is happening. You see that we have a meniscus here. The challenge here is to make sure that the heat exchanges, the evaporation of the liquid, is happening at the top surface of the porous system rather than within the pores. Because if the liquid recesses within the pores, and if it is within the pores that heat is being exchanged, then the heat transfer performance goes down. So the challenge is to be capable of designing a porous system which is capable of maintaining the liquid phase at the very top of the porous element. Okay, that's what we are interested in this work. So we started by considering only the fluid mechanics aspect. That's what I am going to show next. And we tried to, out of those very complex and three-dimensional problems, we tried to understand the very physics and developed some theoretical approaches and wrote our own models. So we said, okay, so assume that we have a constant porosity. So the porosity is fixed. The volume, which means that the volume of liquid within the system is a constant, okay? And we know that the liquid is going to enter from the bottom of the system and exit, go all the way up by capillary suction and exit at the top. How are we going to assemble to create a porous network that will allow to pump by capillary forces the maximum amount of liquid all the way to the top of this element? So we considered different configurations. A very simple one would consist in having an assembly of parallel cylindrical pores. Another way would consist in having a radial configuration like the one that you see here. And we took inspiration from trees. Remember the image that I was showing previously where we had the roots pumping water from underground all the way to the trunk here, bringing them up to the branches and the leaves and evaporation. So we thought, okay, let's try to understand how things are working here. And you see that we have a tiny tree in our porous system in which we will have the true level, the root level, the trunk level, and the canopy level. At root level and canopy level, two options are possible. One is the radial connection between the pore inlet and the trunk, and between the trunk and the pore outlets. And same story on the drawing on the right-hand side, except that this time we are replacing this radial connection of roots by dendritic networks. And we don't do this randomly. It's because basically 25 years of research work have taught us that dendritic configurations happen to be much more efficient than any other kind of configuration when it comes to flowing a liquid from an inlet to an outlet. Okay, so there we had a hint of what could happen. And so 3 examples here: parallel, radial, and dendritic. Same total volume, but a very different way of making the connection. And more or less flexibility in discovering what should be the length of those branches, the diameters, etc. So like I said, this is existing in nature. And now let's see how things work. So if I take just the root level, but all the methodology that we developed works for the entire the trunk and all those other branches. So here you have an example with one bifurcation level, and the system of equation that we want to solve is written on the right hand side. So what we know is that we're capable of expressing in terms of force balance, we know how to express the capillary pressure as a function of the radius of those tiny cylindrical elements. We have gravity effects, and we have friction losses, assuming laminar flow. Okay, so if we are capable of writing that the system is such that the capillary pressure at the very top balances gravity and friction losses, then we know we solve the problem. And we are looking for the maximum mass flow rate, which is expressed here. We look for the maximum mass flow rate. No, we look for the geometrical characteristics, which are radius and length of all those tubes that you see here on the drawing, so that the mass flow rate is maximum. But when we do this, it's not enough, because we are going to obtain a certain value of the mass flow rate at the exit here. And that leads to distribution of the geometry for all the cylinders that we have. But then to this distribution of the geometry corresponds a certain value of the mass flow rate here, another value of the mass flow rate here. And obviously we have mass conservation. So we need to make sure that at the level of tube number 1 and at the level of the cylinder number 2, the geometrical characteristics, length and radius, are such that capillary pressure within each of those cylinders is capable of sustaining the mass flow rate that has been calculated. And we call this the capillary strength. So we need to make sure that that distribution of geometrical parameters for a fixed porosity is capable of pulling the fluid up from the very bottom to the very end. That's the system that we solve in the code that was written by the PhD student. Okay, and here I am showing you some examples of results. Again, we are only considering the fluid mechanics aspect, and we show how those root network are going to develop as a function of the change in bifurcation level. So every little drawing that you see here is the one that corresponds to the maximum mass flow rate that will be extracted. On the figure here, N represents the number of inlets for a given elemental configuration. Next, we compare the results. Again, the porosity of the porous system is fixed, and we are comparing the different configurations, radial, parallel, and dendritic. And as expected, for the same total volume of fluid, so same porosity, the dendritic configuration is the most efficient one, which means that this is the one that will allow to pump the maximum mass flow rate. So that's for the fluid mechanics aspect. But it's not enough if we are interested in evaporative cooling. So now we're going to combine what has been done so far only from a fluid mechanic aspect to the heat transfer part of the problem. And here the question is, how do we design the porous system, which is, number one, capable of pumping the liquid by capillarity, as we had seen previously, but also maintain the meniscus at the very top. And that's the heat transfer part of the problem. So we want to make sure that evaporation, so the phase change is happening only at the top of the porous system without receding, without the meniscus receding within the porous network. So again, we're trying to understand what is happening here, and we take a very simple example and try to write the equations describing the problem and try to solve it and understand what are the key parameters, okay? So here we consider as a very basic element what you see on the right-hand side. So it's just a Y-shaped structure in which we have two pore inlets joining somewhere, which is to be determined. 1 and 2 are joining at a certain location, and the exit is happening through one single port. And when I say that the junction location has to be determined, it is because this is part of the design of the porous system. How do we assemble, in this simple example, 3 tiny cylinders so that the maximum flow rate of liquid is pumped all the way up to the system and evaporation is happening again at the very top of the system. All this will depend on the choice of diameters, length for a fixed total volume of pores. So here is a zoom on the parameters that we are interested in. So you see, you recognize this Y I was alluding to, and we are assuming that we are assembling upside down those tiny elemental systems. The liquid enters from the bottom, will exit at the top and evaporates because the top is the part of the porous system which is being heat by the heat flux. At the interface between liquid and gas, which is the meniscus here, and we do hope that this meniscus is remaining at the top surface, we have here cylindrical elements. The gray part is the solid, the center part is the liquid. The meniscus is represented here, the angle of contact is here. We need to calculate the shape of the meniscus for every configuration. I will explain why. And we know the temperature of the wall. Okay, so this is how this is going to work. So in terms of methodology, we repeat what I was explaining before, meaning that we write the balance between capillary forces, between friction, and between gravity. So capillary, friction, and gravity, we need to maintain capillary strength everywhere. And we search, that's what the equation that you see here is the one expressing the relationship between the radius of a parent cylinder, a parent channel, and the two children channels. Okay, so in this example, that would be the mother cylinder. Those are the two daughters cylinders. And we use symmetry because it's complicated enough. I will open a parenthesis here. The idea that to have the most efficient network, you need to have a certain ratio between the radius of a parent channel and the children channels is something that was discovered more than 100 years ago by two physiologists. One was Murray and the other one was Hess. Hess was the first one. And they were physiologists and they were interested in blood flow. And they were capable of proving that in the blood system in the human body is efficient from a fluid mechanics point of view, because there is a constant diameter ratio between those tubes. That's thus the name of the Hess-Murray law. And people interested in capillary flow wrote that the same ratio was also true for capillary flow. And our work has proven that it's not the case. That the Hess-Murray, it was very interesting because the Hess-Murray law, so this constant ratio, which is the exponent gamma that you see here, this exponent corresponds to the one of the Hess-Murray law, in which the driving force is a pressure difference, because that's the one generated by the heart when you are interested in the blood circulation in the body. That ratio is kept when the porous system is away from the exit, which would be away from the top surface of the porous domain here. But the closer the bifurcations that you see here are coming to the very top, to the exit of the porous system, which is driven by capillary forces and not by a delta P, by a pump, then we lose the constant value of this exponent. So that was one of the very interesting results that we obtained from this work. So anyway, what I'm saying here is that part of the system of equations to be solved is the discovery of what should be the ratio between the diameter of the tubes at every bifurcation level. Okay, that's for the fluid mechanics part, which is something that we've covered previously, but then we are going to add the heat transfer part. And I'm sorry for all those equations. I don't want to scare anybody. Just let me tell you the story. What we are solving here is simply an energy balance. We are saying that the heat transfer between the wall of the cylinder of the pore and the interface, you see the meniscus here, is balancing the heat exchanges at the interface. And the heat exchange at the interface is evaporation. Okay. Next, we know how to express the mass flow rate, which is evaporating at the interface. And that is given by an equation, which is called the Schrag equation, which accounts by a few parameters: the saturation pressure, the temperature of the interface, which is changing as a function of the location on the interface. That's the Kelvin equation, which will give us the partial pressure. And finally, we write here the energy balance. And because we know the heat flux, we can calculate, once we have the temperature changes, we can calculate the heat transfer coefficient. Okay, so that's the system that we solve, and the way it works is this way, because the energy balance has impact on the network, on the poor network generation and vice versa. So we had to write an iterative model that was capable of using the results of the energy balance to inject them into the network generation, and through several iterations we were capable of calculating all the parameters of interest, the main one being the heat transfer coefficient. The work was validated with data that are available in the literature, and I will move fast because I'm taking too much time here. Very quickly, let me just say that we show that we're interested in the impact of the porosity of the design porous material to the flow rate and to the heat transfer coefficient. So that's why I plot here the change of the heat transfer coefficient as a function of the complexity of the network, 2 or 4 levels of bifurcations, 4 different values of the heat flux heating this porous element. That's the change here on the total mass flow rate that the system is capable of pumping all the way up to the top surface of the porous system. I had some slides on a side note, but I will skip it and go through the third part of the presentation, which is the one related to the thermal management of batteries. Okay, so a few things. I will start by discussing the electric vehicle chain, which goes from the vehicle to the charging station, and finally to the stationary battery energy storage systems, also called BESS. All right? So at this level, batteries are necessary. At this level, batteries are also necessary. And every time we talk about batteries, we know that during charging and discharging, heat is being generated. If therefore increasing the temperature of the battery cells, if the temperature of the battery cells goes too high, several inconveniences may happen. The very first one, in case of overheating, will be some losses of performance and decrease in the capacity of the battery. If too much of this is happening, then it will have impact on the anode and on the cathode, leading to the death of the battery. And in some extreme cases, we can experience thermal runaway. And we are all aware of very, how to say, dramatic and spectacular videos of like this one, the bus setting on fire because of thermal runaway, which it's truly runaway. That term is here because it really expresses the reality. Once this is starting, it's just impossible to stop it. And the best solution is just to let it consume entirely. So thermal management is absolutely necessary. And that's what we are interested in here. So let me start. Okay. This is what may happen. So we had we developed some experimental campaign to characterize the batteries and understand better what is happening during charging and discharging to be capable of proposing meaningful cooling solutions. So let's start with the experiments very, very briefly. So the idea is to capable of controlling the load of the battery, charging and discharging, and at the same time that we monitor the changes of voltages, we are recording the thermal changes in 2 different ways. Number one, by thanks to an infrared camera, we are taking some images of the surface of the battery to have a sense not that much of the value of the temperature, but of the uniform or non-uniform character of the change of temperature of the battery surfaces. If actual values of temperatures are of interest, and it was the case here, then we have some thermocouples. Same idea, just to show that here we considered different configurations. In one of them, so in addition to controlling the temperature of the environment around the battery cells, but in one case there was a fan generating forced convection thanks to the movement of air around the battery, and we were interested in having a sense of the impact of the environmental conditions on the heat generated by the battery. And here you have some examples. In this battery, there is the temperature of the ambient was maintained at 25 degrees C. There is no fan around. The battery is discharging at a C rate of 3 C, and you see the change of voltage as a function of time. Those are the corresponding changes of the temperature surface of the same battery. So that battery was painted with a matte black paint in order to avoid any reflections. And here you see that as a function of the depth of discharge from 25 to fully discharged, that's the 100%, you see that the temperature changes at the surface are non-uniform. So there are some hot spots. Those hot spots are occurring in the vicinity of the tabs. And that is important because when it comes to thinking about some cooling solutions, that gives an idea of where to put most of the efforts, which will be in the vicinity of this part of the other battery. And I would like to add that in an ideal configuration, the temperature of the average temperature of the battery should be maintained between 15 and 35 degrees Celsius. And so that's one constraint. And the other one is that, which is related to uniformity. The other constraint is that the temperature changes at any given time at the surface of the battery should be of 5 degrees at a maximum. So which means that the temperature difference between this red spot and this yellow spot should be 5 degrees, which is obviously not what is happening here. Okay, so now here you're seeing the results as a function of the rate of discharge. 3C on the left, 5C on the right. So the faster the discharge, the higher the amount of heat being generated during the process. Here we studied also the impact of the ambient temperature, 25 or 40 degrees Celsius. So you see not that much impact on the voltage change, but a strong impact on the temperature. I will skip this one if I can. Okay, here. And now let's discuss. So, yes, a little summary of what I've been discussing. So here you see the combination of charging, which was at a 2C rate at constant current, and then a little bit of rest. So we let the battery relax during a while, constant voltage, and then this is the discharge phase at 3C at the top and 5C at the bottom. 3C means about 20 minutes to discharge entirely the battery. 5C means 12 minutes. Here, the environmental conditions were 25 degrees C and no forced convection around. So that's what we are measuring. And now in terms of modeling this, and the models are plural, and that's why I insist here, because we need to combine a heat transfer model to calculate the amount of heat that is being generated. And to do this, So the equation that we solve is just the first law, okay? That's conservation of energy. The amount of heat, which is, so the changes within the temperature are balanced by the heat exchanges with the environment and the heat generated within the battery, which is the challenging part, in fact. How to estimate the volumetric heat generated by the battery. What we know is that this term has three contributions. One of them is the Joule effect, which is at the tabs of the battery. The other one is called the irreversible amount of heat. So that's basically the Ohm law, change of its resistance times current square, if you will. And the third term is the reversible contribution to the heat generated, which is called the entropic heat. And it is calculated as a function of the change of the open circuit voltage as a function of the temperature, which is in most of the cases neglected because it's difficult to measure. I have a PhD student right now running some experiments to measure this term. So we just developed a protocol in the lab allowing us to have access to this term and to really answer the question, is this a contribution that can be neglected, yes or no, and under which conditions can we do this? So yes, the question is, how are we going to calculate the heat generated? We know that what the terms are, but to calculate it from a heat transfer point of view would mean that we should be capable of measuring the heat exchanges within the battery. And inserting thermocouples within the battery is extremely dangerous because it can lead to thermal runaway. So the solution is to use instead some electrical methods. And that's where there is need to find a compromise between accuracy and simplicity. What the electrical engineers do is that they plug models, electrical models, to the system to model the discharge and the charge of batteries. And there is one model which is a good compromise between accuracy and simplicity. That's the one developed in 2006 by Chen and Rinkenmora. It is an assembly of resistors and capacitances in parallel that I'm showing here very briefly, which happens to be implemented in ANSYS Fluent in the battery model. Okay, so that will be the open circuit voltage, which is the voltage that you would measure if you let the battery discharge naturally. This is the actual voltage which is measured as a function of the discharge or charging rate that is being decided. This is the current, that's the internal resistance of the battery, and those are the two assemblies in parallel of resistance and capacitance. So that makes a system, an electrical system, which is represented here, in which we, if we are capable of solving it, we will have the change of voltage as a function of time. And that's what we do. So we worked on a model which is solving this electrical representation of charging and discharging to obtain the heat generated. And then we solve the first law of thermodynamics to have the distribution of the temperature within the system. So here I'm showing you the validation of the work with, on one side you have the experimental measurements, and on the other side you have the numerical ones. And finally, thermal management. So this is about inserting cold plates in between the batteries of the cells of a battery pack. What we did here is that we compared different solutions. So we know that as far as liquid cooling is concerned, those plates inserted between cells can be very simple, like the one that you see on the left-hand side. So that's a cold plate through which a liquid will enter from the top side, because that top side will be in the vicinity of the tabs where most of the heat is being generated, and the liquid exit on the opposite side here, bottom right. Instead of that, we could imagine to replace this entire volume of liquid by a serpentine, which is what we're showing here, or by something slightly different, which we call the canopy-to-canopy system, in which you have a main trunk through which the fluid is entering before splitting through branches that you see here in parallel and exiting through another trunk, thus the term canopy-to-canopy, which is represented here in a perspective view with all the detailed parameters, I will say. And as you can see, we have the lithium ion cell represented in gray, and in blue we have the cold plate, very, very thin. And the parameters we can play with here will be the ratio of hydraulic parameters everywhere that you can see here, so that we're trying to minimize the pressure losses, so favor the fluid flow, and at the same time we're trying to improve the heat exchanges to control better the temperature changes. That's something that I am showing here. So that's numerical work, and we're just solving mass conservation, momentum, and energy on the solid side for energy, and all those equations on the fluid side. And you see here how the shape of this canopy-to-canopy cold plate at the top will have an impact on the temperature distribution on the cell. Same story here, in which we are interested in efficiency. So we are looking at the heat exchangers as a function of the pumping power, which is something that we want to have as small as possible. That's the amount of heat that being extracted as a function of time, the black line representing the heat which is generated during the discharge in this example. That's the result at the level of a battery pack. So we have a sandwich of cold plates in between the battery cells. And I will just end here in another example, in which this time, instead of inserting the cold plates in between the battery cells, we thought about another configuration. The battery cells are assembled together within a box, and the cooling, the thermal management is happening at the box level, at module level, instead of happening at battery cell level. So the way it works, we have a cooling system which is at the bases, so right below the cells, and the bottom view of which is here. The liquid enters this way, is then distributed here, and exits there. And this very simple system is capable of controlling the entire temperature distribution within this entire domain constituted of an assembly of battery cells. So to finish, I will just say that the work we do on flow architectures finds applications in various domains, from the cooling of electronics to energy storage and water harvesting, for example. But we are also interested in the design of bio-based materials to control moisture transfer, something I didn't cover this afternoon. And applications go well beyond thermal engineering, because we are also working at the prediction of the blood flow through organs and more specifically through the liver. So a very completely different domain, but where the methodologies that we develop can find also very interesting applications with the help of people specialized in health sciences. And my last word will be a thank you very much, and especially to all the young and bright researchers who are working with me on those topics. Thank you very much.
Thank you very much, Professor Lorente, for your presentation. So I'm going to give time for a couple of interventions of questions. So you may start. Okay, Professor Ramos, go ahead.
Thank you very much for a nice presentation. And I have very many questions, but just to focus on one specific topic of your description is when you explain this project on cooling something by pushing a liquid towards an edge and then evaporating the liquid. It seemed to me that this situation is very much what you have when you're trying to dry food. Essentially, let's say a piece of bread or whatever. Then you put some heat on top, and then water starts migrating towards the top and then evaporates.
Yes.
And if you do this in a proper way, then you will have kind of a conservation of the food because it is drier than it normally is. So I would like to know whether you have thought about this application, or if your models can be adapted to this this other more biologically inspired situation.
So I think that you are absolutely right. This is the in terms of physics, it's the same type of problem. I have not worked on this, but I think that what we're trying to do is that we're trying to engineer those the porous assembly so that it is adapted and allows the right level of evaporation at the top surface for a known heat flux. In what you were saying, the problem is different. I guess it would be more about knowing. So it's about drying some, I don't know, bread or potato. I have no idea. But the porous system is not a degree of freedom because it is what it is. So it would be the research question would be more about what is the allowable heat flux, what's the best one that will allow to dry enough but not too much, because in this case that would threaten the quality of the food, I think. The question would be different, but the writing the set of equation describing the problem would be the same. Very good, very nice question.
Thank you very much.
Thank you. And last one, Professor Sergio, go ahead.
Thank you very much for your nice presentation. It was for me very interesting. And I was wondering on this problem, in the same problem where you have the porous material, and you mentioned that in this case, when you made these models for different tubes, you mentioned that the dendritic configuration is the optimum, or it is the best.
Yes.
But I was wondering if this, if you think that you have a lot of tubes, in this case, you increase the viscous dissipation. So if you think in a naive way, you may think that that the more tubes you have, the more viscous dissipation you have. So in this case, you have an optimum number of tubes. You have to calculate this optimum number, or how is it explained that that when you have this dendritic configuration, you have the optimum performance?
Yes.
I'm not sure if I am.
I think so. I think you will tell me if I understood correctly. So I think that what you're saying is that while the complexity of the network is increasing, if we have more and more bifurcations, we will have more and more locations where we have local losses.
Yes.
And it is true that the way you saw the set of equations, when we design the network in terms of friction, we account only for linear friction, the friction along the tubes, not at the bifurcations or at the junctions. And there is also until when are we allowed to do this? There is in our previous work, we tried to work on this very question in different ways. So what we did is that we solved those problems numerically, 3D CFD. So modeling Navier-Stokes in 3D through the entire system. And when we do this, then we account for all those local losses. And comparing to the analytical approaches, we could find the limits until when are we allowed to do this. But then we came up with a non-dimensional number that we call the Svelteness number, which was a way to catch the impact of the shape, the global shape of the network. And so that's this Svelteness number is a ratio. So it's a non-dimensional term. It's a ratio between internal and external length scales. And by doing this, it's like a geometrical parameter, if you will. We could show that if this non-dimensional term, the Svelteness of the network, is high enough, which meant, if I remember correctly, above 10, then it's okay to neglect the local losses. When it comes less than 10, then we have to account for the losses. And like you said, that may change the conclusion.
Okay. Okay, thank you very much. And just a small question. You are thinking in this application only for water, or could be another liquid?
Oh no, it could be any other liquid, as long as we know the characteristics, so density and viscosity.
Okay, that's right. Okay, thank you very much. Very interesting.
Thank you.
Thank you. Well, with this, we finish the seminar. Thank you, Professor Lorente, for your presentation, and thank you all for your attention.
Thank you. Thanks a lot.